Hello everyone. Okay, thanks for tuning into this optional video on proving why e of ax plus b is the same as e of x plus b, and why var of ax plus b is the same as a squared var of x. What you can see here, and what I've drawn, is a probability distribution table and we're talking about here at the moment DRVs, so discrete random variables. And you can see that our values of x are ranging from x1 all the way to just some random number xn, where n is an integer. So first things first, we need some definitions. We know that sigma, where I is going from 1 to n of sigma of n going from I to n of the probability of x equals xi, so i.e. what we're saying is that as we sum up these values in the table, we know that probability is always going to add up to 1. There's our first thing here. We're also building on the idea that for our expectation, remember, expectation is the same as x lots of p x equals xi. And also remember this is our e of x here, and also we need to remember that e of x squared is the same as sigma I going from 1 to n of x squared p of x equals xi. Once we've started with these premises, we can begin to prove these things here, where a and b are constants. So I'm just going to move that over here and let's get going. So we're saying that e of ax plus b is the same as sigma I going from 1 to n, and this time x isn't x is ax plus b, times the probability of x equals xi. Let's multiply that out then. So we get sigma I equals 1 of n, we get ax p of x equals xi, plus sigma b lots of p x equals xi, x going from I going to 1 to n again. Here, as we know, this a has nothing to do with I, so that can come out, and we've got x p of x equals xi. And similarly, b has nothing to do with I, so b can come out. I equals 1, n, probability of x equals xi. And remember, this is capital, this is small. Where does that leave us? Well, as we defined from the start, we know that xp of x equals xi is the same as our e of x. And we know that as you sum all the probabilities together, they're always going to equal 1. So we are left with a e of x plus b, as we wanted. So we're happy. Let's do the same now for the variance then. So we want to prove the above. So we'll start with var of ax plus b, and this is, again, we've got from our variance formula, which we know that var x is the same as sigma x squared, probability of x equals xi, I going from 1 to n, subtract our mean squared, isn't it? Our expectation squared, which was sigma x p of x equals xi, I going from 1 to n, all squared. So let's build from that premise. So we're going from here. In fact, let's move that down a bit. Now we've established that. So we're going var ax plus b. X is no longer x. We're replacing that with ax plus b. X equals xi. I going from 1 to n, minus sigma, and again ax plus b. P of x equals xi, and this is all squared. I going from 1 to n. Well, where can we go from here? And remember, this thing is all squared. Where can we go from here? Well, we're going to have to, first off, expand this thing out. So we're going to get a squared x squared plus 2ab x plus b squared, and this is all times probability of x equals xi, I going from 1 to n again. And then what about this squared thing here? Well, I'm going to do exactly what I did before, but we need to build on what we did in that previous slide. We know that this thing here is e of x all squared. Well, ax plus b all squared, remember. This is e of ax plus b all squared, which we learned earlier was the same as e of x all times a plus b. So that thing is all squared here. Let's carry on. So this time, we're going to expand this thing out again. The a squared can come on the outside. We're getting used to this now. We've got x squared p of x equals xi, plus, and here 2ab can come out. 2ab, I equals 1 to n of x, p of x equals xi. And we've got our b squared term here as well. So plus b squared sigma p of x equals xi, I going from 1 to n. And this is all subtracting our statement here. So minus our a e of x plus b all squared. Now, just finish that off. Okay, so let's tidy this thing up. This thing can stay the same. So this is a squared I 1 n x squared p of x equals xi. Note that this is already starting to look like what we're aiming for, something to do with this. And remember, this is our final goal. We've got this thing, x, p, x equals xi. We know that's the same as e of x, don't we? From before, this x, p of xi. And now we've got to deal with this thing here, the b lots of p x equals xi. Well, sigma p of x equals xi, that's adding all the probabilities together, so that's just going to be 1. This thing equals 1. So plus b squared. And now we're going to subtract this thing squared. So if I multiply out the brackets, I get a squared e of x all squared plus, sorry, we're going to minus now, aren't we? So we got minus 2 lots of ab e of x, and we've got a minus b squared. This is starting to look really good because b squared cancels. 2ab e of x, 2ab of x all cancels, and we're left with, if I take a factor out of a squared sigma I equals 1 to n x squared p of x equals xi minus e of x all squared. And hurrah, because this is our variance equation. This is var x, and so we are left with var x, and we're happy. So, just one quick example then. What we have here is that given that e of x is 3 and var of x is 2, and that we've coded it now with this value y, so everything has been times by 3, all the data has been times by 3, and then 2 has been subtracted from it. We want to find e of y and find var of y. Okay, so let's do that then, using what we know, because we've already built up our proofs. So when we say e of y, we are actually saying e of 3x minus 2. And since we know that e of ax plus b is the same as a e of x plus b, this is the same as 3 e of x minus 2. And we know that e of x is already 3. So 3 lots of 3 subtract 2 give us 7. E of y must be 7. Similarly, var of y equals var of 3x minus 2, which we know from our earlier proof that var of ax plus b is the same as a squared var of x. So therefore, 3 squared var of x. And we know that var of x from here is 2, and so therefore I have 9 times 2, and our final answer is going to be 18. And there we go. So, simple use of coding, and we've proved where it came from. Thanks very much.